underrepresented if there weren't a set of lectures focusing on them. And that's where we are. So it will be about symmetries, right? Now, actually, I find that subject symmetry classes in semiconductor. Can you
turn on the microphone?
Yeah, I would, but
you have to press that.
No? No?
Yeah. I think the battery is on. Maybe just move it up a little higher.
Yeah.
Sure.
All right. Okay. Next question. Is that okay? Yeah. Larger?
Yes.
Yeah? So I find that's a subject which is not easy to motivate in one or even two sentences. And hence, let me begin by sort of outlining the basic setting in which we will operate. And once we have done that, it will be easier to kind of motivate and structure what we are going to talk about. So one thing is comparatively easy. It's going to be about electronic conductors. And for me, electronic conductors within the framework of these lectures is something like that. So we consider a chunk of metal. Somewhat later, in I mean maybe the fourth or end of third lectures, we will touch upon topology, and then we will consider insulating systems as well. But for the moment, a metal. And I assume that the system is non-integrable. I mean, the single particle dynamics inside is non-integrable in the sense that there may be some impurities around which scatter, or there could be chaotic boundary scattering. So non-integrable single particle dynamics. That's essential. Non-integrable. No, you see, I'm starting that's small again. Next thing we want to talk about the metal, so we put fermions inside, right? So there's fermion. And we also allow these fermions to interact. Now, as far as interactions, I'm putting this in parentheses because, I mean, interactions are not exactly destructive to the story I want to tell. I mean, interactions are always there, but we will not focus specifically on ultra strongly correlated systems, right? I mean, so think of some weakish interaction and, or think of this as some kind of thermodynamic system, yeah? So about exotic strongly correlated phase. So an ordinary chunk of metal. That's our system. Now, how do we approach the physics of such a system in general? There's not too much that can be said, but one thing is clear. We can organize the different types of dynamics and physics realized in such a compound hierarchically according to a range of increasing time scales, or more or less equivalent to increasing length scales. So imagine you have here an axis and you plot in some units time or unit length. And then there are a number of, qualitatively speaking, there are a number of distinct regimes we can identify. And the first of these is, I mean, this is very sketchy and qualitative, what I'm telling you. The first of these relates to microscopic length scales. By microscopic, I mean length scales shorter than the length scales where the system actually begins to feel that it is non-integrable. Yeah? Shorter than, say, impurity scattering path, or shorter than, more generally speaking, some Lyapunov times or lengths. So these are, if you will, you could call microscopic scales. And the Kosovar length scale relevant here, I mean, you know it in a sloppy way, is some kind of scattering time of impurities, if you want. Scattering time. Or speaking in the language of length scales, this would be some mean free path. All right, so on scales shorter than that, the dynamics is, if you will, it's microscopic and it's governed by, of course, by some kind of Hamilton operator. Yeah? So there's some unitary dynamics. Unitary is important here. Unitary quantum dynamics. and it's mediated by the underlying system Hamilton operator. And on these scales, you can actually typically forget about the presence of disorder, or other instances that rise the system into chaotic dynamics. But at a somewhat larger time scales, the system begins to feel that there is chaos around it, and some kind of chaotic scattering sets in. And then we enter a regime where the dynamics goes effectively irreversible. I mean, in a Buddhist point of view, or manner of speaking, it's of course still governed by some unitary quantum evolution, but effectively what you will see is irreversible dynamics. In most instances, this will be diffusion. But you could also think of a small nanoscopic quantum dot where there is no diffusion, and yet you go effectively irreversible because the dynamic is classically chaotic. Sort of, yeah, what I think. So, for lack of better terminology, I note it here as a mesoscopic, regime. And here we have effectively the irreversible dynamics. And this irreversible dynamics is governed by some effective evolution operator, which in most cases we will be discussing is the diffusion operator, but the more general technical term is the Frobenius operator. I mean, if you have not heard about these guys, think of diffusion if you want. So it's Frobenius. And this guy now tells us what particles effectively do. Now let's suppose we wait longer still. At some point, if this is a finite system, classically, the dynamics will have become fully ergodic. I mean, a charge carrier put in, think of classical Grave-In, would have fully explored the accessible phase space, or the energy shell that is accessible to it. And from that time on, which we could call the ergodic time, and I noted it's gamma. The dynamics is fully ergodic and becomes, in the sense of chaos, totally structureless, the classical dynamics. Yeah? Energy shells are fully ergodically filled. And there is a length scale associated to that in a kind of thinking about a diffusive conductor. This would be the system size, actually. Yeah, you need to diffuse all the way through the entire system. It's classical for the moment, you don't touch quantum mechanics here. And only then you go ergodic. In the time-space domain, gamma would be the inverse of the lowest non-vanishing eigenvalue of the Frobenius operator, or the inverse of the lowest non-vanishing eigenvalue of the diffusion operator. And you could call it Thouless time, but physically it would be the time it takes to make your way through the system. All right, so these are, and here the dynamics becomes ultra-universal in a way. In the sense that, in a manner which we will discuss, all microscopic details on dimensionality and whatever does no longer affect the dynamics. It's only symmetries that are left, which, and we go there in a second. Okay, so that's pretty much a setting, and this here would be the kind of macroscopic vision. Again, it's not a good word, but you know what I mean. So that's kind of the setting. Is that sort of clear? All right, so now what do we do with this? One thing we can say is, in an ideal world, I would put this in these. Is it okay if I
So a lot of what you're saying is not important that it was electronic conductors, right?
No.
This could be spin transport.
Yeah.
Could be, So that's the
Yeah.
example you're using, but the physics is
we're in the
more general.
superclass. Yeah.
Good.
Sure. This much more general.
Yeah.
All right. So, now another axis I can draw. We can ask ourselves, what are the fundamental kind of dynamical principles that are relevant to describing physics in the respective regimes? Yeah? Of course, this is a very sketchy question, and the answer is also sketchy. But it's probably safe to say the following. Here, and also to some extent in here, microscopic details like scattering rates, differences between transport and and absolute scattering and all such stuff matters. So, in a manner of speaking, we could write this here: microscopic details matter. Okay. Now, as we go to larger length scales, the system begins to forget a lot about underlying microscopic dynamics, and it's more like macroscopic system parameters that are of importance, and often these are then encapsulated in some phenomenological constants like a diffusion constant or whatever. So it's microscopic details become less important. What remains important here is dimensionality. Whether you are dealing with a 1, 2, or 3-dimensional system is extremely important, as everybody knows. So, say here, and then finally, if we go to the longest time scales, you can think what will remain. I mean, what kind of dynamical principles remain that tell us something or that classify different types, fundamentally different types of physics, and it's essentially symmetries. And we have to be much more precise about what we mean by symmetries, but all of you have certain notion in mind. And mind you, what I do not mean by symmetries are the classical unitary symmetries like translational symmetry or rotational symmetry or stuff like that, which easily go bust. I mean, they usually go lost here. But there are anti-unitary symmetries, which we will discuss, which are much more robust and which play a very important role down here. Oops. To the extent that this symmetries. People have been telling us, I mean, or that's at least the way I grew up, that down here symmetries and only symmetries are of importance, period. It's a description of the quantum system. Now, question to you, will this statement remain undisputed or? I mean, I could try to sell it to you like that. Everybody agrees?
Why would the dimensionality still remain important?
Look, I can give you a technical or non-technical answer. I mean, the non-technical one is, think classically. I mean, you are in some kind of 3-dimensional or 2-dimensional system, and now and you have some phase space and some energy shell. And at some point you're fully covered. I mean, every point in phase space is uniformly covered. You have maximum entropy in the system. Simply have forgotten about the dimensionality. Dimensionality matters as to how fast do you get there and how much time does it take. So, but once you're there, once you're in the fully ergodic regime, dimensionality is lost.
What about topology?
Yes, topology. So that's of late, people have been talking a lot about topology, as everybody, I mean, you've all heard about that. And topological principles remain very robust all the way down to the largest time or length scales. Yeah? So topology is become another player. Let's see, perhaps I can, because I want to, so this is here topology. And to the extent that topology and symmetries these days, they come as a package. You should think of them as twin principles. And we will spend quite some time in elaborating on the connections. Topology also means that dimensionality, which used to stop here, now remains important all the way through. Because from a topological point of view, it matters quite a bit as to whether you are dealing with a 2- or 3-dimensional system. And I'll explain how and what. Yeah? Okay. Yes, that's basic.
How? Sometimes people talk about random matrix theory, so is that, where is that?
I'm getting there. So far it's only principle, random matrix theory comes next. Yeah. Provided I try to chalk to do that. No? We are out of chalk. So, as to Leo's question, the next question I want to bring up is, given this kind of scenario, what kind of tools do we have in our box to actually attack such a system? And of course, the tool you're using depends a lot on where you are, right? And well, here, in this regime, what we usually do is we apply different types of, this is now about tools, all kinds of perturbative methods, which come in different shapes and colors. I mean, there could be old school Russian diagrammatics, or you do semi-classics, and if you are working in quantum chaos, or another type of perturbative expansion that allows you to describe cross sections, and maybe you can make it into the diffusive regime and talk about diffusion modes. But it's quintessentially perturbative and tailored to the short to medium time regime, right? So let me, summarily write this as denoted by diagrammatics. But, and we'll discuss examples. Then there is a complementary regime where only symmetries matter, and here, or used to matter before topology came up. And here there is an old paradigm due to Wigner and later Dyson, where you argue as follows, that touches on the question which was just asked. Given some Hilbert space which you quantize, and some phase space which you quantize into some Hilbert space, and the phase space dynamics is fully ergodic, then what do you do on the quantum side? And the idea was to write some maximally random maximum entropy type effective phenomenological operators, and we go there. I mean, we'll discuss it. But the framework is random matrix theory. That's how it's called. And RMT is strictly limited in its applicability to the ergodic regime. So the RMT. And then, somewhat as of the beginning of the 80s, we have something yet more powerful in our box of theoretical concepts which you can apply, which actually covers you can argue where we begin, but somewhere here all the way through, and that's quantum field theory. And you have had an exposure of quantum field theory by Anton, but we will go there again, maybe from a slightly different perspective. For the moment, let's just note that there are quantum field theoretical methods which really cover a whole lot of this kind of axis. Okay. So that's basically the setting, and now I'm in a somewhat better position to tell you what we are going to do. So everything here is anchored on the unifying principle from which we want to look at this symmetries. And what I would like to discuss is, first of all, how do we understand symmetries? I mean, what are symmetries? How do we get them under control? Next point is, what kind of phenomenological consequences are caused by non-conventional or non-empty kind of symmetries? Then I will spend quite some time on kind of discussing quantum field theories, or the way how quantum field theories are determined in their structure by essentially symmetries, and more or less only symmetries. And that's important because once you have symmetries here, you might say, here, down here, everything depends on symmetries, but what here? And the point is that symmetries, the importance of symmetries radiates out into this regime. Or more technically speaking, the relevant soft modes of the quantum field theory are to a large extent determined by the underlying symmetries. And we want to understand how. Yeah. And what can you do with these theories? And then finally, I want to kind of venture into topology. Yeah, at a certain point. I mean, maybe in the third lecture. Actually, it depends a lot on the pace. I mean, I'm duly intimidated. Victor told me that it's an extremely bright company. Everybody could give the lectures instead of me. It's just I will. Usually, I tend to be slow and talk a lot, but I guess I will try a somewhat steeper pace, and you slow me down. Or we can do it the other way around. I slowly. So, but somehow we have to find a pace, and that the thing is open-ended. We can stop anytime. Yeah. Good. So now, maybe somewhat more specifically, how will we organize this discussion? We already introduced a number of players that are relevant here. There is random matrix theory. Then we have diagrams maybe, or perturbation theory, which also play a role. And there is a linkage between these two, which I want to discuss, which is rather instructive to understand. And we also already argued that somehow there is a more comprehensive or general concept, quantum field theories, which connects to both diagrams and RMT. So there's a conceptual connection between these two. And then there's a fourth player in the game, which I haven't mentioned so far, which is, it's not meant as a hierarchy, just it's rotational invariant here. It's math. And, okay, now mathematics classifies to a large extent what goes in the mathematics theory. It also has a lot to say about quantum field theory. This connection is somewhat in there. And I will begin here. So from a group dynamical perspective, that's the worst way to start, right? So I'm promising you 90 minutes of extremely dull and technical discussion. And that's how we start. Given the long weekend and so on. But I hope you could agree at the end that it's good to have a solid kind of groundwork to work on. So I hope it will be well invested time, but it will be boring and dull, I promise. Then we ask, what are the phenomenological consequences of this kind of mathematical exposition? And it will turn out that random matrix theory is a good platform to discuss this. And in particular, the diagrammatic reinterpretation of random matrix theory. So that will tell us how we can understand symmetries in an intuitive way, in terms of soft modes and so on. And the advantage here will be that this kind of block is applicable to pretty much any system you could think of. I mean, it's a rather general discussion. And from there, we will then venture into quantum field theory. Plan and everything after that is open. But once we have that, we can start discussing. I mean, ideally, I would give you a brief introduction to topological insulators, and then we can, and Dirac operators, and we can then discuss this in a symmetry-oriented language. I just don't know how far we can get. Actually, question: differential forms. Who feels comfortable with differential forms? Be brave. I mean, answer. Am I allowed to use differential forms in a kind of, so in a wishy-washy way, then it will speed up our discussion at some point, essentially. And so we will try. I mean, all right. So let's start in earnest. Symmetries in quantum mechanics. We really start from scratch. Symmetries in quantum mechanics. What I'm giving you is a kind of softened exposition of a much more hardcore representation of subjects in this paper. And it's 04056. Yeah. And the working goal of this discussion will be to make it from textbook representation of symmetries to a concept known as symmetric spaces, which is kind of important here. Maybe before we start, one word on the style of these lectures. I generally emphasize concepts over applications. Yeah, so I don't expect really high-powered applications, but I really want to express concepts, and in doing so, I will try to approach the relevant concept from as many different perspectives as I can. That also implies that the discussion will be superficial at times. Yeah, so we will hop around, and maybe sometimes stuff will lack a bit of systematics. But I learned that it's kind of a good way to look at this from different perspectives, and I'm trying to communicate with you what I found useful and skip what I did not find so useful. Yes, and do ask questions, more than you are asking now, but maybe everything is clear so far. So, we start from the following data. We want to do quantum mechanics, right? Given the basic data we start from is given a Hilbert space. And I will denote it H. And in this Hilbert space, we have a Hamilton operator. So this was Dyson's originally kind of input data from which he started. It sounds, I mean, what could be more general than that? We are doing here the first capital mistake. And you can try to find out in what sense, but I'll tell you, in this way we will not be able to chart the entire kind of framework of symmetries that's available. And this starting point is kind of flawed. But Dyson's original point of view in the 60s or 50s or whenever they started was to start from here, most general Hilbert space, most general Hamilton operator. And let's see how far we can get. Yeah? All right, now then we assume the existence of a symmetry group. Now, what is the symmetry group? The symmetry group is simply a set of mappings which operate in H such that the following two conditions are met. We expect the Hamilton operator to be compatible with the symmetry in the sense that it commutes. I mean, like such H. And then there is a mild additional condition which we impose. We expect our symmetries to be, I'm not even sure whether it's a condition, but it's to be norm-preserving. Yeah, a rotation or translation will not then change the norm of the economic state. So, norm-preserving. And that then leaves us essentially with two options. I mean, these maps representing G can be represented in Hilbert space in terms of either unitary operators, unitary to the job, or anti-unitary. Yeah? And I'll explain to you what. Yeah.
So excluding the conformal?
Oh, conform. Yes, I will not talk about conformal in the following, but I'm not sure why conformal is norm-preserving. Is that a problem?
Yeah.
I mean, for the time being, first of all, I want to think about finite dimensional Hilbert space here, so I don't want to touch all these things with infinite dimensional. But conformal map is no. Okay, probably you're right, but yeah, right when you have dilatations and stuff. But okay, let's. I'll be there. I mean, no conformal symmetry in this section. So there is our good old friends at unitary maps, which are kind of simple, so unitary G's. And unitarity means, as you all know, we have a Hilbert space, so we have an inner product, and hence we can write down the following condition. And within this group of unitary symmetries, we can distinguish essentially between two subclasses. There are unitary maps that can be homotopically connected to the identity. Think of a rotation, you can always smoothly undo a rotation. And some which you cannot, and a reflection. Yeah. Something like that. So there are transformations. As I'm writing, like I said, this was all done in the last 2 weeks, and the negative side effect is I cannot hand out nicely tagged notes. You know. But what I will try to do is, I have some reasonably well-organized handwritten notes, which I will try to copy. I'm saying try because I'm writing in a nanoscopic script size, and it's pencil, so I'm not sure if you manage, but if yes, then you get it. Okay. So you don't, yeah, whatever. Transformations. Uniformly connected to the identity in Hilbert space. And yeah, I mean, rotations, for example. And then there are transformations not uniformly connected. And we can think here of reflection. Okay. These are the unitary transformations everybody knows about. Now then there are the anti-unitaries.
What do you mean by uniformly connected? You just mean discrete?
I mean that you can extend this to a family. I mean, a one-parameter family of transformations, some parameter, and you can play with this parameter continuously and deform it to the unit matrix. Okay? Yeah.
an example, sorry, is an example of a continuous symmetry which is not uniformly mountable to the identity? Unitary.
Yeah, a reflection of space.
That's not continuous. That's
Huh?
discrete.
It's not. Yeah, well, but what is meant by continuous? Continuous more or less a definition of this, right? Well, when you say continuous, then you have to say can be continuous depending on some parameter, right? And of course, you can. Okay, now we can. There can be symmetry groups which have different connectivity, symmetry manifolds which have different connectivity components. Is that what you are?
You could define a continuous set of operators which are a reflection and a rotation. It's not smoothly connected to identity.
Yeah. Thanks. Yeah. Good point. And so we have. Let me call this G tilde for a moment. G tilde. How would you read this symbol? Victor, it's a psi. It's not a chi. Victor always blames me. He tells you it looks like a chi. What?
If you had like this.
Okay, my chi. It would.
Context is clearly
It's a nice chi. This is definitely a psi. But so the anti-unitaries. So here we have that G tilde acting on psi. And G tilde prime is just changes the order, right? You've seen that before. Okay. Which is the same as psi prime complex conjugate. Now, why do we need these anti-unitaries? The prime example of an anti-unitary mapping is time reversal. Important symmetry in quantum mechanics. A corollary of that here, I should say, an immediate corollary is that G tilde acting on a wave function times a complex number, or a state complex number, is complex number, complex conjugate pulled out in G tilde. So that's a consequence of the definition. And so anti-unitaries, complex conjugate complex numbers. And an example why we need this or want to have this, just to remind you, is let's think of the following. Suppose we monitor the time evolution of a quantum system. And then in the time-dependent Schrödinger equation, we have something like this here. But time is not really, it's like a parameter in Hilbert space. It's not really like a sequencing of it as an operator, and yet we want to change time. And the most economic way of doing it is just to change this I here. It leaves the d by dt untouched. So at least that's a sloppy way in which I rationalize it. So that should be, that's a condition, I d by d minus t, and that is the same as minus I. Okay. So our symmetry group, and it's a group because products of symmetries are symmetries again, has unitary and anti-unitary maps in it. And let's now try to think, what can we say about the structure of the symmetry group in the most general terms, without using any kind of additional information. And there's actually quite a bit of what can be said. A few simple observations. So let's define the group G naught, which is in G and I. Should tell you symmetry group I will denote as capital G and in its symmetries. So this should be the unitary subgroup in G.
Question.
Yeah.
Why do you call it a unitary subgroup?
I define it. That's the definition. G naught is the G naught in G naught we have all those transformations about Hilbert space which are unitary by definition.
Oh, I see.
It's a definition. Definition.
Sorry.
Yeah.
Is it Is it true that no anti-unitaries are uniformly connected to the identity? Or do we have the same?
I guess so, yes. How would you? Essentially, the story I want to tell you in a second is that there is essentially only one non-unitary, anti-unitary map, modulo unitary. And yeah, ask the question in 2 minutes, or maybe. So G1, which is also a subset of G, will be the anti-unitary subset in G. It's not a group. Because if we have two anti-unitaries, G tilde and H tilde, element G1, then follows that their product is unitary. Yeah, and hence they do not form a group. And this tells us actually more. Namely, you can do the following: you can pick one element out of G1, one element of your liking, which you prefer, and then generate the entire set G1 by multiplying this fixed element with all the unitaries you have, and then you get them all. Yeah. So another consequence is that if we pick one element, P, like time reversal, but it could be any other anti-unitary, right, out of G1, then we can let's say that G1 equals T times G0. Yeah, and you just multiply this. Or another way of saying is you can say that you obtain all the symmetries by considering the coset space G1 modulo G0 times G0. So that coset here, if you divide out all the unitaries, if you consider the anti-unitary essential of G1, yeah, which is one element, this contains either nothing, I mean the identity, or our reference element as an orbit. Yeah. I guess what I'm telling you in complicated ways is there is essentially up to unitary transformation only one element in the anti-unitary second. Yeah?
So that part of the board is not readable.
Is not what?
Like
yes.
Yeah, like past this heating. Yeah.
There's not much written here anyway. I mean, it's no, it's what I said in words. I mean, keep in mind one anti-unitary map, and all others are unitarily connected.
Oh yeah, I just meant like in the.
Okay. So let's then go a little bit further in this direction and just pick one element out of our. So what we want to we want to pick one element which is nice, from which we generate all the rest. Yeah. So we assume that we have a T element G1. And what I will assume is that's a mild assumption, that it's actually an inversion. An inversion in the following sense. As between inversion, which simply means that if I square our anti-unitary operator, which is again unitary, I get a complex number times the unit. I mean, just right. Now,
so that's no longer
it
just
should be,
that's no longer just time reversal?
Nope. I mean, it's not. Well, I mean, it could be also charge conjugation.
Right.
So
you're just calling it T, but
I'm
it
calling
doesn't
it T.
necessarily
Yeah,
mean time
it's
reversal.
right, but
Okay.
I will use T later. I would want to argue at a later stage that starting from T, I get all the others like charge conjugation and so on by playing with T and adding something to it. Now we want norm preserving, right? So that has to have unit modulus. So that's actually a phase. Yeah. Otherwise, we have problem with norm preservation. And now let's look at the following. We can say more about that. Namely, let's look at T cubed, which we can write as T squared, or equivalently as T squared T. But T squared is Z, yeah, e to the I phi. So that is e to the I phi, and that here is also e to the I phi. But now we act with T on e to the I phi, and that is complex conjugation. Yeah. So what we require is that, oh no, I have to stop right now. E to the minus I phi equals e to the I phi. And that means that e to the phi is plus or minus 1. Yeah? Got it? I mean, follow me. So that, so we know that our, no matter, I mean, we haven't used Campbell or whatever, but whatever anti-unitary we start with here as a reference, if it is an inversion, then it must square to plus minus the identity. In both realizations, as you know, both scenarios are realized in nature, spin and non-spin, yeah? Good. Good. So that is, I guess, all we can say in the most general terms. Questions up to this point? Nobody's asking questions. Thomas got lots of questions.
I think I have a very stupid question.
Yeah.
So is a reflection of time and reflection of space actually generated by the same anti-unitary up to a unitary?
The reflection of time. My instinctive reaction would be, but maybe it's not a good way to be instinctive. In a relativistic setting, I would say pretty much yes.
With the reflection of space, you say it was unitary.
Yeah.
Yes, in a normal conventional. Reflection of space is unitary operator. Perhaps we get to Dirac operators, and then maybe it's a good way. I find it difficult to think about it now.
We're talking about regular quantum mechanics with Hamiltonians.
Yeah.
So Lorentz invariance, even
Yeah.
if it's there, is heavily disguised.
Yeah, right. It's not there. That's yet. Right. Later, okay, I shouldn't make such a mystery out of it. The flaw here is the good setting has Fock spacing. So Fock is an additional structure. And when we go to Fock, then a whole new universe comes out. But so far, we're in this Hilbert space. Yeah.
So we are assuming that the coset G1 by G0 has only one element in it?
It's not an assumption, it's a statement.
Okay.
It has two elements. I mean, the trivial element and the one
Okay.
which is generated by an unitary. Yeah?
So does that mean that only one of these options for the is realized at the time?
Yes, if you are operating, that's a good question to ask. Next one, we go now to, we will reduce out our symmetry representation spaces. And then we will see how this works. Okay. Now, we will proceed now under a certain working philosophy. Yeah? And that philosophy entails the following kind of conditions. We assume that G is given to us. We know G. We just know it. Then we want to kind of classify Hamiltonians which are compatible with G. So we will ask, what, given the structure of G, what can we say about the structure of the compatible H's? And then we will reformulate that question in the language of time evolution. We will not so much focus on the Hamilton operator as such, but we will focus on the time evolution generated by them. So that sounds like a superficial statement. Who would, Hamilton operator, time evolution, e to the I Hamilton operator is the time evolution. So it's pretty much an empty statement. But it's important because historically the focus was on the Hamilton operators and their invariance groups given a certain symmetry. But once you make the seemingly trivial extension, we go to focus on the time evolution operators, then the statement of the structure of symmetric spaces is around the corner. And that will tell us a lot about, a lot more than we would get just from the more historical perspective. Yeah?
So where here are we talking about groups and where are we talking about the representations?
We talk about representations now.
Okay. So, so what does anti-unitary mean not in the context of the representations of the group?
Keep this question for a while. I mean, we'll discuss now exactly how these structures are represented in our interface. Right. When did I start? 10 minutes past the hour? Slow. All right. So what we discuss next is kind of a warm-up to the extension of these rather general and abstract concepts to something more kind of concrete. Oh, that's a joke. And as a warm-up, let's discuss a setting where the set of anti-unitary symmetries realized in our problem is empty. So no time reversal invariance, no anti-unitaries. Let's talk about. And then we are left with G equals G naught, and that's a unitary group, an abstract unitary group. And what I want to tell you is, or convince you of, is that given the scenario which I just erased, this G naught essentially contains empty information. It doesn't tell us much. So the unitary sector of our symmetries we can discard of as far as classifications are concerned to a large extent, and I'm telling you now in which sense. I mean this, yeah. And that now has to do with representations. Namely, so G is, I'm using a semi-formal language here. I don't want to go very formal. But what we can say is that G is represented, which is G naught, in our Hilbert space in terms of unitary representation matrices. In HS. Now we all know that given a representation of a group, it's a good idea to go to irreducibles. I mean, like, think about rotations. The first thing you would do, go to a different angular momentum sector, stuff like that, right? So what we have is, once we went to an irreducible representation, all our elements of G naught are represented in terms of block diagonal matrices where the different blocks contain the different pillars of the. And let me do it right like this. So this here is meant, these dots are matrices, and they correspond to equivalent representations which can, however, occur in higher multiplicity. So think of a spin system. So each spin has a fundamental SU2 representation, but there's lots of them, so you get more than one representation. Yeah. And then there will be a different angular momentum sector. You can get another one. So you get block matrices of that sector. Each little symbol is an irrad of your group, but they can contain higher multiplicity. Okay. Now, suppose you have now here N1 blocks, and here you have N2 blocks, and here you have N3 blocks, and so on. So this is counting the different multiplicities. Then there is a statement that our Hamilton operator should commute with this structure, right? We know that. I mean, that's a condition. We know that G, H, G inverse equals H. But these are irreducible representation blocks, which means these are full matrices. If you go through your group, you get, I mean, there is no redundancy here. And that tells you that our H has to act as an identity operator within each of these little blocks. So H is a matrix in this space, the residual H, the symmetry reduced H, but does not contain structure within the blocks. The formal statement behind is Schur's lemma. That's an essential point, but I think it's like, and I might make it more concrete in a second. But the statement is that, yeah, maybe we can focus on one of these blocks for a moment. So think of this as a sub-Hilbert space of the entire structure. And what we can then say is that this would be the tensor product of the representation group of G, I mean this little guy, yeah, tensor some reduced Hilbert space which is n1 dimensional. And that's where our H acts. Yeah. So tensor some, I don't know, some H. And that has dimensionality in H equals, say in this case it's n1. Okay. And accordingly, our Hamilton operator H acts trivially in the first sector and acts as a reduced Hamilton operator in the lower sector. Now, once you went to this irreducible setting, once you're here, the only thing about the symmetry is now taken into account, right? And the most general H, which will be compatible with the symmetry in this sense, will be just the Hermitian matrix for this little H. So what I want to say is get rid of these unitary symmetries by reducing them out, use this Schur structure, and then you are again left with something void of symmetries. Somewhat sounded void, I think to formulate, but I mean maybe an example which you...
So this is just the structure of the block up there you called N1.
Yes. Here this is N1, is, I mean, our little h would now act in some C3 complex three-dimensional.
And then you're going to show the structure when you put them together in 1, N2, N3?
Yeah, sure, then I come there next. But this was just one block. Maybe one example, I mean, when you, the way we formulate this in quantum mechanics, when we have a symmetry, say you have rotational symmetry, right? The first thing we do is, so we have some SO3 symmetry, and then we argue as follows in the textbooks. We would say that in our Hilbert space there live wave functions, and these wave functions can now be classified according to angular momentum sectors. Right? So we have something like psi classified by angular momentum quantum numbers. They specify the contents of this representation here. And then you put some kind of, maybe some radial quantum number, or this could be infinite or finite dimensional. And that is now that is the Hilbert, or is the variable which indexes the Hilbert space in which our H acts. A rotation invariant H would act on R and not on U. Right? So, and that was a somewhat more formal way of putting this. And the statement is that yeah, we say that the dimensionality of these reduced blocks, if I call them n for a moment, at least n1, un, the unitary group is a set of maximally symmetry, is a maximal set of symmetry compatible time evolutions of our Hamilton operator. So set of time evolutions and that answers the question I have been formulating before. And if we do not have anti-unitary symmetries, a maximal set of time evolution operators that are compatible with the one remaining symmetry we have left, and the ordinary hermiticity of quantum mechanics is UN, not a big deal, right? You knew that. But we will see in a second why the structure is useful when it comes to more complex symmetries. Yep. So the question was, what is when we go beyond one of these blocks? I mean, we can write down an almost obvious extension to the full matrix here. So we are about 50 to 60% through the dial mathematics part in the orientation. Tomorrow will be just picture drawing. Right. So more generally, I write down the extended structure. Yeah. We decompose our full Hilbert space in terms of the different representation spaces of the symmetry, which are these little spaces that sit in here. And let me call this, I mean, there would be a first space, and then the second, and so on. Maybe it goes on here. And then the residual contents of the theory, the symmetry protected, sits in a smaller, in the Hilbert space, it's counting the multiplicity, or accounting for the multiplicity of the orientation. This is it could be just one-dimensional or higher dimensional.
Little h is now,
little
h has an arbitrary matrix now? This one. That's an arbitrary.
I'm telling you that once we have taken into account rotation symmetry in this way, we can, in the radial sector, we can do whatever we want.
So that's the radial sector?
Yes, that's the radial sector. Yeah.
And actually, so I think usually, I guess this is what you're going to speak about, is about these Lie groups, or Cauchy space and so on. infinitely finite dimensional. On your example, it's infinitely dimensional. Yeah.
No, think of it as we cut off someone. We have some higher energy. We don't want to go angular momentum above a certain. Everything here is philosophically it's finite dimension.
Maybe I'm wrong. So this n dimension of hn, is it so h, little h x on r, you said, right?
Yeah. Yes, in this absolutely right. In this example, you would actually be in absolutely you would be in infinite dimensional setting.
Yeah, that's what.
But then put it on the lattice.
Okay.
I mean,
okay.
Yeah, it's a good point. Yes. Sure. Right, and now we take the direct sum of all these spaces, and that then represents our Hilbert space. Our Hamilton operators acting in this are correspondingly the direct sum of our little guys corresponding to different vectors in this space. So 2 plus. And our manifold of permissible time evolutions are, it should have said that, we define M in words is the manifold, and it's a smooth object, so it's really a manifold, of symmetry compatible time evolutions. And our M always lives in some big master unitary group, right? It will always be a subset. It has to be unit, but it will be submanifold of the unitary group. And here, in this case, our M is now the Cartesian product of U's acting in the different sectors. So U and 1, U and 2. So we have here products of unitary here, unitary there, unitary there. Good. So if we look at this, we see that somehow the entire story is split into disconnected sectors. They don't talk to each other in the present setting. So we can, in this unitary case, we can just focus on one block and we are done. Yeah, there is not much more to say. Now you may ask, why make it so complicated? Why introduce these different representation blocks and so on? In a second we go to the anti-unitaries. And then we will, I mean, to anticipate the interesting question will be whether an anti-unitary acts within these representation spaces or whether it walks you from one to the other. And there are several prominent historical mistakes in the recent literature where this point was not properly taken into account. So that's why I think it's well invested to do this. Yeah.
Is it immediately clear that I can choose an arbitrary H1 and an arbitrary H2 without them being correlated at all?
No, if they belong to different representation spaces of your symmetry group, they will by definition not talk. There's a strong selection rule that prevents them from talking. You cannot have matrix elements if you have rotational symmetry between spaces of different angular momentum, right?
There are no matrix elements between them, but certainly they're given by the same microscopic Hamiltonian and they're correlated.
Sure, of course. Once you have one big Hamiltonian and you went to the irreducible representation, your H is fixed, this H structure. But I guess I would, okay, that's again, it's a good question. I guess it would be fair to say that within this most general setting, I can cook up pretty much any operator here without violating any Pauli principles.
But it might represent a microscopic Hamiltonian that's kind of ridiculous.
Totally weird.
What about restricting to locality?
Locality.
Local operators?
No, there is no reference to space here or whatever. I mean, this is, if you want to impose locality as an extra condition, and then of course you may get extra conditions on H. But this could be also a complex nucleus, and I mean, which is as non-local as it gets. And look, maybe the philosophy is I'm trying to be ultra general here. Yeah, so I want to use no more than that, and then cook up the most general structure, and then we can talk about zillions of restrictions. Let's see.
So I thought that the decomposition H is rotational across small h was just that you decompose it between the anti-unitary form and the unitary one?
No, no, no. Here, for the time being, everything is unitary. Here, it's strictly unitary. In the last 15 minutes, there was no mentioning of anti-unitary. All right. So before we move on into this anti-unitary sector, I mean, we extend our symmetry. Let me give you one kind of working picture where a double composition is realized, where we have just two of these spaces, and that is the following. It's not about rotations now.
No, can you say before you go on? Can you say so? If I look at one sector, then I can't tell what's the overall symmetry, what overall symmetry I came from. That just like on unitary evolution. Unitary.
I didn't get it.
You know, if I confine myself to a particular sector,
yes.
let's say, for example, L and M, then
yes.
I just have some. I can't tell that what the symmetries of the full system
yes.
are.
I would agree. If you have only that
it's
information.
Only the structure of the whole. It's only in the structure of the whole Hilbert space that's a tensor sum and product. That's the point that you don't involve unitary, anti-unitary.
No, first of all, nothing is anti-unitary here.
Right.
I'm using as much of unitarity as I'm dealing with a finite dimensional Lie group, and I can go to its irrats. The unitary group does the job for me, so I can do that. And once I'm at the level of the irreducibles, the line of the argument went that then we have our little sub-operators acting in this multiplicity.
They all look the same.
Huh?
All symmetries look the same. As long as they're unitary as opposed to anti-unitary, they all look the same. Once I specialize to a particular irreducible representation.
Yeah, but it could also, my symmetry group could be a subgroup of the full unitary group, right? And still I would go to the irrats, which then might look a bit more complicated or different. I want to, you said symmetries, I mean in this G0 sector are Lie group symmetries in most cases, and I have my irreducibles, and I can use this language. I mean, and then I do not get interesting stuff out of that. So a picture, an example which I would like to suggest, and we will come back there. You all know that, I mean, recently there has been a lot of activity on kind of interesting kind of Fermi surfaces in 2 dimensions, and in particular people are working on 2-dimensional systems, higher dimension, but 2 dimensions, in particular with Dirac points, I mean, low energy quasi-particle islands. And then we have the following kind of schematic setting. So suppose you have a Riemann zone, 2-dimensional, essentially 2 torus, but and then you have certain momenta here. So here say you have 0 momentum. And suppose you are dealing with a system such that you have low energy islands of quasi-particles around. P-wave superconductor would do the job, of graphene, topological insulators, surface things. Yeah? You've all seen such. So schematically, I want to say that suppose you have 2 sectors. And then we go to low energies, and what we're interested in is restricted Hilbert spaces here and there. So importantly, they will be characterized by one center momentum, and Dirac islands come in pairs. So there will be non-vanishing momenta, and often you have an inversion that gets you from one master momentum to the other. So you've all seen that. Now, one setting where we could run into such a situation is if there are residual unitary symmetries acting here, then we would have 2 disconnected Hilbert spaces. And that could, then we could, I mean, it would be very natural to write down such a decomposition for your Hilbert space that it's a direct sum of that space and that space. Why do I mention this? We'll see it in a second when we talk about topologies. Yeah? So in this case, again, I mean, our time evolution manifold would be Cartesian product of that time evolution here. Okay. So now we go one step further and introduce anti-unitaries. And So now we consider, yeah, think really for concreteness about time reversal. It could be a different one, but physically I really want to address time reversal now. The time reversal invariant system. And then we know that our G1, the set of anti-unitary symmetries, is time reversal operator times G0, and it is different from 0. Now, how does time reversal act? Time reversal will map our Hamiltonian to TH T inverse. This was the structure in the beginning. G H inverse, now specializing in T. And I call this representation tau. Technically, it's the adjoint representation of the time reversal operator. But the symbol tau means just this. And notice that we require that this here. And notice that tau is an involution. Side remark. So, or even though t squares to plus minus 1, tau always squares to 1. Okay. Now, what about our time evolution operator? How will they respond to tau? The answer is clear. The induced time evolution will be or let me write this as x minus I. And h bar is 0. So what will happen to this guy? Well, it goes to t x minus IH t inverse, and now you see what happens. T leaves h untouched, but it changes sign. I, so it becomes x IH t, and that is u inverse, and that is reassuring because that's exactly what we expect. Time reversal should undo time evolution. Huh? So our good time evolutions will have definitely this original tau. Yeah.
I missed your comment about tau. What is tau versus t?
Tau is t acting in an adjoint representation on an operator. So it's a symbol when you an operator gets transformed under tau, it means write down t operator t inverse. T is an operator acting in Hilbert space, and that's like what we always do in operators transforming.
Okay, that's how it's a transformation. Tau is just a transformation.
Yeah, it's a transformation of operators as opposed to the transformation of states. Thank you. Now comes an interesting question. We have now this structure, and now we can unleash our tau operation and ask what will it do with how will it transform these spaces? And there are essentially two options now. If you call these different, we have these guys, these little h's, right? And tau doesn't talk to this unitary sector of the theory much, but it does something, it works here. And now we can ask ourselves the following question. Having t act on a Hilbert space H I, essentially with full packaging, what will happen? Now, in principle, in the worst case, T will warp us around in the entire, will produce a complete mess. But intuitively, we don't expect that, right? So what could happen is that we remain in our Hilbert space, remains invariant. But it can also happen that you go to a different one. So, in pictorial speaking, time evolution applied to some guy here gets you to another representation sector. Now, let's explore how this happens and why, and what's the meaning of that.
Can't it mix? Can't it mix?
It cannot. It's a non-trivial statement. It's a very good point to bring up. And why can it not mix? So why do you get, in principle you could get a direct sum of, it could be a complete mess on the right hand side. But we have the following nice structure. Let's do the following. Let's take, let's act with the unitary sector of our, so that is, I'm mixing some notation, but that's a unitary transformation acting on the time involuted Hilbert space. So let's write on this. Yeah? And the question I want to address now is this here, is this an invariant space? So, if this condition is met, then we know that the unitary guy acting on this stays in this space, and that means that this here must be in a proper representation block. Huh? So we need to check this condition. And how do we do that? We apply T once more. So we can apply another T just for the fun of it. We can do that. So we get T U T H I. But T squared is plus minus 1. So the equivalent statement is this here. Because T squared is plus minus 1, so it definitely remains in H. But this is unitary. TUT, I mean, this is unitary. And we know that these are invariant subspaces. So the condition is okay. So whatever we do is we wind up in a fixed representation space of the unitary representation. That's an important statement. I mean, time evolution doesn't create a complete mess. It just may hop around here between different blocks. Yeah.
So HI and HI prime can be of different dimension.
Once more?
The Hilbert spaces HI and HI prime.
Yes.
They have the same dimension. The dimensionalities.
I guess so. Yes. I thought about it. Yeah. I mean, it would be weird to go from spin 1.5 to spin 3. It should be the same dimension, but they could be different. I mean, they can still transform differently under.
Can you please? Please repeat what was the conclusion from TUT being a part of G0 also?
Here. I know that whenever G acts on Hilbert spaces, the unitary group, it stays in that Hilbert space. Okay. And since it is unitary, we are granted this condition. Okay. So we can read it backwards, and hence conclude that that one will get you will be compatible with the general structure of the unitary set. Yeah.
So then how can it go? So that statement, how does it say if I apply the T to HI to those different HI?
How that can happen?
Yeah.
I'll give you an example.
Okay.
It happens, for example, here. You have when you do time reversal, you go from K to minus K.
They necessarily come in pairs. T of HI prime goes back to HI.
Yes, because in evolution problem.
So you only pair.
Yeah.
You don't make any more complex.
No, you right, exactly.
Either singlets or pairs.
Yeah, exactly, precisely. Yeah.
Just like the most familiar example is going n to minus n, like say with angular momentum.
Yes, indeed. That's the most.
At the time reversal.
Yeah, that's what I tried to say here. You go from K to minus K, and these are different. Yeah. It all sounds terribly trivial, right? I mean, K to minus K, we all knew that. But again, you look into the literature, it can be very confusing. Good. Yeah, so that was actually maybe the most tricky part of the entire story. Now, let's do the following. Let's do the following, yes. Given this here, we have now two options. Either I prime equals I or not. And let's go through these one after the other. What I want to tell you is that I is not equal to I prime. I is not equal to I prime. Then you don't get additional information. You stay in your boring unitary world, essentially. But if I equals I prime, new things. Right? So, assume I. And as David just said, I mean, it's really sufficient to focus on pairs. So we can operate in the following simple setting. We know that our we know that before we start talking about time reversal, our manifold was, symmetry manifold was just given by the product of two unitaries acting in the respective sectors of Hilbert space with Cartesian product. And that means that our time evolution operators can be written as block matrices. U1 acts in little h1, hi, and this acts in hi prime, and without loss of generality, we can call them 1 and 2. So that's boring. Now let's ask what tau does to the whole thing. So tau acting on U equals tau acting on U1 and U2. But now we know that this time evolution piece, it changes, it flips the Hilbert space sectors. So it will be, the matrix we get is this tau U1 now acts in the second sector. So we have something like that, tau of U1, U2. But then we know, and that's a holy principle, that that by all means has to be the inverse of U. Because we know that time evolution, that was the most general thing we said, no matter what, I mean, it has to be the inverse of the original matrix. So we have to have, this has to be U1 inverse and U2 inverse. And now we know what time evolution does. It gives us a condition between, say, U2 and time evolution of U1. They are mutually time reversed, right? So that's something you would have guessed. It's not a big deal. So we know, concluding from here, is that our operator has this structure, tau U1 inverse. And that's the conclusion. Yeah, I mean, the most general time evolution of two time reversal conjugate pairs has to have this structure. And that means that the time reversal compatible manifold has a structure U1 originally. This U1 can be freely chosen, but the other unitary is unfixed. It's just nailed down. So the product of tau U1 inverse. So in our picture with this Bringher zone, it's kind of, if this system is time reversed invariant, yeah, then we can do something in our first island. But what we are doing in the second island is unfixed because it's time reversed invariant, and we know precisely knowledge of one tells us what goes on in the other end. But we are still working in a unitary framework. So we have somewhat less unitary freedom to play with, but it's still unitary, nothing more. It's a kind of interesting or somewhat counterintuitive story or structure. Imagine in your head what happens if you switch on impurity scattering between these islands. Then they connect, yeah? And then we have one big Hilbert space, and time reversal would not leave it. Then we are in the second scenario, which we discuss now, and we get a higher symmetry. So somewhat counterintuitively, switching on impurity scattering can enhance the anti-unitary symmetry of the problem.
So M is now U1 cross U1 dagger, basically?
Not exactly. It depends a little bit on what tau exactly does, this guy here. So it could be that, could be actually a little bit more. And it depends on, yeah, it's not, no, like, it's more like transpose. Okay, now that was that. So the bottom line here is to wrap this up.
Actually, can I, here you said M was the manifold, but sometimes you're talking about elements on the manifold, right?
Oh, yeah, I see. Sorry, I meant that.
And same thing at the top.
No, that's okay. That is the Cartesian product of the unitary group, and in it live these things.
Okay, so you put it over there, yes.
Yeah.
Okay.
Okay, so bottom line, up to this point, we have we learned how to do this when things are unitary. We know how to describe them more or less in terms of block structures. If we have time reversal in addition on board, we see that we have discussed one scenario in which we get different sectors of Hilbert space which are mutually time reversal connected. Now,
Can you say, I can't quite, the lower block of the U, you said U2?
Tau acting on U hat U1 inverse.
I thought U2 is the inverse of U1.
Now, here?
No. What is U2 an inverse of U1?
It's tau on.
I maybe not.
So this here. So invert, do the inverse of this, and you see U2 equals tau.
So the inverse is on.
Yes.
Another second parenthesis.
Yes.
You inverted.
Exactly. I apologize. The notation is somewhat heavy here, but actually, maybe how one should approach this. Nobody can remember all these things. I mean, I cannot. Well, maybe there are people who can, but I can certainly not. But it's good simply to. I mean, the take-home story is see what kind of concepts are floating around here, right? So this, if you need to work with them yourself, you can dig it up. Just like it's doing one paper, but I just want to introduce the concepts. The relevant and the most important comes now. That is the case I equals I prime.
Actually, I don't have a very nice question, because the line that you're just erasing, what it says that tau acting on the time evolution operator produces the inverse of it.
Yeah.
Now you're applying the second inverse on that U1. So how does that?
But these are different. No.
It's not acting in the same space.
Yeah, exactly. Yeah, that is how tau acts, and it's more or less defined by it. Look, I mean, in practice, when you work with this, we'll see examples. You never have to worry explicitly what this is. I mean, the theory it just tells you. You get an answer automatically out of it. But the important thing is this you can choose, or that one, and the other one is then enslaved by the concrete way in which your time evolution operator acts, which in turn depends a little bit on the basis. I might have emphasized it. The way
bottom line is that tau acts in the U1 cross U2 space, and the inverse is taken just in the
yes.
U1.
And I should have said that earlier. The way time reversal acts is really heavily basis dependent. Say this complex conjugation you have when you work in the real space basis. Go to momentum space, and then it's p to minus p, different forms. So all this is only representation dependent if you really want to work out in concrete form. So now I equals I prime. Now we can make the notation, I mean, go to somewhat compactified notation. You see, now we are working once and for all in one of these blocks here. Yeah, so there is no need to carry on with this heavy notational structure. What I will do is I write instead of little h the sub-Hamiltonian. No, the little sub-Hilbert space I call again capital H. Just change of notation. In our little h I call again Hamilton operator. Yeah? So we are working in one of these spaces. So the unitary symmetries have been dealt with at this point. They are out of the game. It's only about the anti-unitaries. And we have, just to summarize, we had this little, the operation of time reversal, which does the following on states. It acts by the action of T, and on operators, it acts as T, H, inverse. On general operators, not necessarily H. Then we also know, I'm just summarizing here what we need. We also know that our time evolution operator can be generally written as a product of a unitary and complex conjugation. So K is just complex conjugation. And we learned that T squared equals plus minus 1. And you all know that both situations are realized in nature. So let me briefly remind you of this. So that's t squared equals 1. It's what we have for spinless particles in general. I mean, in concrete applications, so spinless. And then you can always find, let me write the language of wave function. Then you can always find a representation where your wave functions under time was just changed by complex conjugation. Seen that before? Huh? And that is then by definition k. Right? T squared equals -1 is, on very general grounds, is what we have for spinful particles, spin 1/2.
You mean spinless and spinful, or do you mean integer spin and half integer?
I guess I mean half integer.
Okay, and the upper one is integer spin.
Yes. Yes. Okay. You know what I mean. Yeah.
Well, no. It's
no, but yeah, no, you're right.
I wanted to clarify it. Yes.
Not spinless, but
integer spin.
Yeah. That spin Z. No, nobody can read it, but thanks. Yeah. Right. So let's quickly see how or recapitulate how this comes about. I mean, how it works. We know that now we are saying, let's focus on the spin 1/2 case, and then we know that Hamburger flip spin. That's necessary. That's what it has to do. So we know that T acting on spin up, spin down has to be equal to what? Well, spin up becomes spin down, and then we also complex conjugate. That's always true. It's spin up. But we may also have here a phase. And since I have problems with my Greek alphabet, this is my eta. It's a phase. So that we can in principle should also now. Now I want to write axis. And we can write it out like this. A unitary matrix acting on the spin up complex conjugate, spin down complex conjugate. Okay. And that is now by definition, that is UK. Now I'm again, is it spinner now? No. Yeah. It's UK acting on the spinner, right? On the original spinner. So U is defined by this phase matrix. Now we know that T squared has to be equal to -1. And that means that fixes you this unitary these spaces essentially. So what you get is that from T squared equals minus identity, you know that U equals 1 minus 1, which is I times sigma 2 acting in spin space. So here we have case where we get squares to -1. That's now the representation of Hamburger. I just meant to say they are both realized, yeah? Both situations. Now, yeah. What's the policy here? I get my 10 minutes, which I started late, right? So I'm on time still.
Right.
Now Glassman overdrew half an hour.
now I'm fine.
We can do the following. I do it like I do it in my own lectures at home. I overdraw a little because I would like to get, but then you get the time back next time. Next time we will ask you not to.
How much time do you need?
I'm telling you 5 minutes, but you know how to speak.
It's fine. We don't want to miss lunch.
No. I do it like this. I go quick, and next time I recapitulate. And so I want to have the symmetric space at once on the platform. And then you're always so curious about symmetric space that you will ask lots of questions. Okay. So what I want to do is now simply, it's basically, it's no big deal. I mean, just a few formal lines which tell us now what invariants under time evolution, either way, it's, in the case where it's complex conjugation or complex conjugation becomes a unitary, implies for our symmetry manifold. It's a very obvious construction. So classifying n time evolution manifold, and we know that tau u has to be U inverse, and U equals x minus IH t. And we also know that tau h equals h. And now we have the extra privilege of exactly knowing what k is, tau is, namely it's complex conjugation or complex conjugation times symplectic. This guy is sigma 2 I times sigma 2 is sometimes the symplectic unit matrix. So let's first consider the case t squared equals 1, where t equals k. And then we know that this here simply means that h has to be equal to h complex conjugation, because it's invariant under the action of complex conjugation, right? So it's complex. It's a real matrix. Now let's look at the actual generator of time evolution, which modulo this t, which is a boring number. Let's look at this operator, x equals I times h. Yeah, so that's essentially what the generator of time evolution, modulo sine is. What we know about this, following from here, we know that x star equals minus x. Because of this line. Yeah? That we know. We also know that x dagger has to be minus x. It has to be anti-Hermitian because h is Hermitian. We are operating in the unitary group. Yeah? So we can put these two conditions together to conclude that x transpose equals x. X has to be a symmetric matrix. Yeah? And e to the x is our m. E to the ih or e to the minus h. So what can we say about that now? We can say that x, it's a symmetric matrix which is the opposite of an antisymmetric matrix. So in a formal way of writing it, x lives in the Lie algebra of the unitary group, and these are the anti-Hermitian matrices. But we want to get rid of the anti-Hermitian guys. So we remove